So we've had a look at the equation of motion for the restricted two-body problem and derived the trajectory equation, which gives us quite a bit of information about the shape of a particular trajectory or the size of a particular trajectory and where the spacecraft is along that trajectory. We're now going to add to the tools that we've already collected, and we're going to do that by having a look at the conservation of specific energy and the conservation of specific angular momentum. As we're doing that, we're also going to get our first glimpse into the relationship between the position of a spacecraft in its orbit via the true anomaly and the time aspect, just the first glimpse. We're also going to get a glimpse of the orientation, namely the flight path angle. And as we do this, we're going to demonstrate Kepler's three laws along the way. Just to get us started off on the right foot, we'll write down the trajectory equation, which can be written down, for example, in this form. And the trajectory equation describes all of the conic sections. So it describes an ellipse, it describes a parabola, describes a hyperbola. Circle is a special form of an ellipse. So we automatically, by the derivation of the trajectory equation, have demonstrated Kepler's first law. So we're now going to take a look at the conservation of angular momentum. And we're going to do that by taking the equation of motion, and we're going to cross r into that equation of motion. So that looks like this. Now that's a simple operation, and if we look at the right-hand side, we effectively have some non-vector quantities, some scalars here, and r cross r. Well, r cross r is just 0, which means that r cross the second derivative of r with respect to time is equal to 0. Okay, well, r cross the second derivative of r with respect to time is nothing other than the first derivative with respect to time of r cross r dot. And why is that so? Well, that's just the product rule, isn't it? The derivative of the first one crossed with the second one plus the first one crossed with the derivative of the second one. And there we have it, because this term, a vector crossed with itself, is 0. So what we have is r cross r dot here in the parentheses, and the derivative of that is apparently equal to 0, which means that if you integrate it, that is equal to a constant. Now, what we can do is write the r dot vector. We can write that as the velocity vector. And as we've just said, if you integrate it, then it's a constant. And that constant we call h, which is the specific angular momentum. Now, why is that the angular momentum? Well, if we look at what the angular momentum is, it's nothing other than the moment of the linear momentum, mv. And if you take the moment of anything, that's the position where this second vector starts at. So we have r cross mv. And because we're going to work with the specific angular momentum, we divide h, the angular momentum, by the mass to get the specific angular momentum, the h vector, which is r cross v. And because we know that the specific angular momentum is constant, and it's perpendicular to both the v velocity vector and the position vector, that means that the plane which is defined by the r and the v vector is constant in space and perpendicular to h. So the motion is in a single plane. So let's consider the specific angular momentum a little more closely. First of all, we're going to look at the situation here where we have the path of a particular spacecraft, and the position on the path of that spacecraft is indicated, of course, by the position vector r. And the angle that it travels through in a particular amount of time we can call theta as a general angle. And we're going to look at the velocity vector of the spacecraft along the path. And the velocity vector has two components to it. A component along the radius vector, so we'll call that VR, and a component perpendicular to the radius vector, we'll call that v theta because it goes in the direction. And v theta plus VR is v. So if we consider the specific angular momentum again, which is r cross v, then by this definition, the two components of v, we have r cross the sum of vr and v theta. Okay, well, we can expand the parentheses, so that becomes r cross vr plus r cross v theta. And r cross vr, well, r and vr are going in precisely the same direction, and therefore this quantity is 0. Which means that the h vector, the angular momentum, the specific angular momentum, is just r cross the v theta vector, the component of the velocity that is perpendicular to the r vector. And if we look at the magnitude of the specific angular momentum vector, well, then that's nothing other than the magnitude of r times the magnitude of v theta, the perpendicular component of the velocity. Well, and v theta is nothing other than r times d theta dt. Okay, so that gives us then r squared d theta dt. And as we've already discussed, the specific angular momentum is constant. So this quantity is a constant. Now the fact that this value is constant, the specific angular momentum, and therefore r squared theta dot is constant, that'll be quite handy in a moment, because we're going to consider the area shown here. In other words, the area that's swept out by the radius vector. But this area here, that looks rather large. So let's first consider an extremely small angle. And that's one that we can deal with more easily because it's the shape of a triangle. Now, if we consider this triangle where this is the radius vector and here's the angle theta, which will be extremely small, then this side has a length r cosine theta, and this side has a length r sine of theta. Okay, so now we're going to consider the area shown here. The area shown here is nothing other than 1/2 the base times the height, which is r squared cosine theta sine theta. All right, now what we're going to do is figure out what happens when this angle theta becomes infinitesimally small. Well, we get a dA and that's 1/2 r squared d theta. Well, because for an extremely small angle, the cosine of theta, an extremely small angle, the cosine of theta becomes essentially 1 in the limit, and the sine of theta approximates theta in the limit. So for a very small angle, the sine of theta is essentially equal to d theta. All right? So when we consider the amount of area that's swept out per unit time, the amount of area that's swept out by the radius vector per unit time, well, we've just seen that for an infinitesimal amount of time, this is the area. That is to say, 1/2 r squared d theta dt. But if we look at the result that we obtained previously, we'll notice that it's just 1/2 the magnitude of the angular momentum, the specific angular momentum. And frankly, as we've seen, that's constant. And what we've just shown is that Kepler's second law is true. The amount of area that's swept out in equal times is constant. So we're now going to take Kepler's second law and adjust it a little bit so that we can integrate for the area if the radius has swept out a full 2 pi radians, 1 full revolution. And for an ellipse, that means that the time has gone from, say, time 0 to the end of the period. So we're going to integrate over a time period that is 1 full period. Now, if we do that, here we end up with the full area of an ellipse, and the area of an ellipse turns out to be pi times a times b, where a is the semi-major axis and b is the length of the semi-minor axis. And if we integrate the right-hand side, well, h is a constant. That's the specific angular momentum. So we have h over 2 times the integral of dt. Well, that turns out to give us the value of the period. Now, after a bit of manipulation with the properties of an ellipse, the geometric properties of an ellipse, we discover that if we solve for t, then that gives us 2 pi times the square root of a cubed over mu. And this is how we calculate the orbital period. And having shown that this is how you calculate the orbital period, we've at the same time demonstrated Kepler's third law. And Kepler's third law states that the square of the period is proportional to the cube of the semi-major axis. We're now going to take a look at some of the relationships between the VR and v theta. And in particular, we're going to take a look at this angle here between the velocity vector itself and the v theta vector. And we're going to call that angle gamma. And the name of that angle, gamma, is the flight path angle. This is an important angle because we need to consider at times the orientation of the spacecraft. And we're going to do that with respect to these two axes, VR and v theta. And v theta is also known as the local horizontal. In other words, it's perpendicular to the radius vector. A natural question to ask is, how would we calculate the flight path angle gamma? Well, turns out that gamma is an angle in the triangle whose sides are v theta, VR, and V. So we can take the tangent of that angle gamma, and that's, of course, nothing other than VR divided by v theta. All right? Now, as we've just mentioned, the velocity vector, that has two components, VR and v theta. And since they're vectors, when you add them up, of course, you get the velocity vector. That also means that if you wanted the magnitude of the total velocity vector, then thanks to Pythagoras, you would just take the magnitude of the radial component of the velocity and square it plus the magnitude of the transverse component of the velocity and square that. Fine. Let's take a look at each of these components then, because if we want to calculate the flight path angle, then we might want to know a little bit more about each of these components. So we'll first take a look at VR. And VR, just to point out, is nothing other than r dot. Now we're looking at scalars here. It's important to be very clear about when you're dealing with a vector and when you're dealing with a scalar. If we take a look at VR and we say that, well, that's nothing other than r dot, dr dt, then what you can do is you can take the trajectory equation and take the derivative of that with respect to time. Now, if you do that, the derivative of the trajectory equation with respect to time, then after some manipulation that we won't demonstrate here, you end up with the following expression, mu over h times e, the eccentricity, times the sine of theta. So if you need to calculate the radial component of the velocity, then this is the expression that you use. What do we know about v theta? Well, we've already seen that that is actually r times theta dot. All right? But we know something about the specific angular momentum, namely that that is a scalar r times v theta. Okay, so that means that this quantity here is also h over r. Now, and if we fill in the trajectory equation for r, then we end up with the following. Mu divided by h times 1 plus e cosine of theta, where for the moment the angle theta we've included as the true anomaly, which would normally be indicated with the letter nu. All right, but given these two quantities, the two components, we can now develop a relationship to calculate the flight path angle gamma. We're now going to develop an expression for the conservation of energy. And in order to do that, we're going to take the r dot vector and dot it with the equation of motion. Now if we look at the left-hand side, we can observe, because we've seen this manipulation before, that is nothing other than 1/2 the derivative with respect to time of the r dot vector dotted with itself. And on the right-hand side, we have minus mu over r cubed times r dot. And that's a relationship we've also seen before. All right, now let's, on the left-hand side, let's write this as 1/2 ddt. And all we're going to do here is write the r dot vector as a slightly more familiar v. So we have v dot v. And on the right-hand side, we're just going to cancel out the r's. So we have r squared, and here we have r dot, scalar quantities. Okay, now on the left-hand side again, we just have 1/2 d dt. And in parentheses, we have v dotted with itself. Well, that's nothing other than v squared. And on the right-hand side, we can make the observation that the expression here is nothing other than the first derivative with respect to time of mu over r. You can check that for yourself. It only takes a moment. Okay, now on the left and the right-hand side, we have derivatives with respect to time. So we'll just bring all of the terms to the left-hand side, and then we end up with the following. So the derivative of this term with respect to time is equal to 0. Now, all we'll do is integrate both sides with respect to time, and we see that this term here, v squared over 2 minus mu over r, must be equal to some constant. And that constant we're going to indicate with an epsilon. The constant there turns out to be the total specific mechanical energy. And that's slightly easier to see if we take a look at each of these terms. This term here will look a whole lot like 1/2 mv squared, but the mass is divided out. That's because we're dealing with specific quantities. So that term there is nothing other than the specific kinetic energy. And this term here is the specific potential energy, where we've chosen the 0 point, the 0 reference point, to be at infinity. So where r is infinity, that's where the potential energy is 0. Anything closer than infinity, and you have a negative specific potential energy. So this equation here represents the conservation of energy, in this case written in the form of specific mechanical energy. And it is also sometimes referred to by another name called the vis viva equation. Now, given this term for the conservation of mechanical energy, which we've just demonstrated, we can observe that on an orbit, the mechanical energy is conserved. Therefore, at every point on the orbit, the energy is the same. The only thing that's different is that for a different radius, different position, you have a different speed. And this turns out to be an extremely handy tool in our arsenal, in addition to the trajectory equation and specific angular momentum. It would be quite handy, actually, to be able to characterize an orbit based on the amount of energy in that orbit. So we're going to take this equation and develop it slightly to come up with a handy value for the mechanical energy for each orbit. So let's take a look at that. E is v squared over 2 minus mu over r. Now, since on any orbit the total value of this is the same, we can consider the right-hand side at any point we like. For example, at perigee. So we'll fill in the velocity at perigee, or periapsis, if you will. And if we're able to fill that in here and there, then we end up having a total value, which is the total mechanical energy of that orbit. And it's true anywhere along the orbit. Now, what we're going to do is we're going to use the fact that the magnitude of the specific angular momentum is RP times VP. We're going to use this fact in transforming this equation. So instead of writing VP squared, we'll replace that with the value of H squared over 2 RP squared minus mu, and we're going to multiply by RP here and in the denominator as well. So we've just multiplied by 1 there. All right, so that's a first step. Now we're going to make use of the following relationship, namely that the semilattice rectum is equal to A times 1 minus E squared, but we know that it's also equal to H squared over mu. In addition, we're also going to use the fact that the radius at periaps is equal to A times 1 minus E. All right. Now, if we do that, then we can get rid of the H term. We can also get rid of the RP term. We end up with the following. Now, with a bit of additional manipulation of these expressions, which I won't write out in excruciating detail here, this term, you can check for yourself, can be reduced to minus mu over 2A, which means that the total energy can always be expressed as minus mu over 2A, and that means that it's determined entirely by the length of the semi-major axis. That determines the energy of an orbit, regardless of what kind of orbit it is. So the vis viva equation, the total specific mechanical energy, is written as follows. And this equation is valid for all conic sections